Hello, so welcome to the online lectures for Math 152. This is the midterm 2 review class. As you will no doubt be aware, the midterm is not taking place on Wednesday as it was originally scheduled. It's now going to take place on Friday as an online assessment, but nevertheless the topics for the midterm remain the same. So in this review class we are going to go through a series of questions related to the topics that are going to be tested on the exam itself. So let's get started, and we're going to start with question 2, which is a series of different integrals that we're going to calculate. So first of all, let's take this first integral here. This is the integral from 0 to pi by 3 of x sine x dx. So this is a definite integral. And if you look at the integrand here, this is a product of two terms, and it's an integral that you want to look to solve by parts. So our u here, we're going to take to be x, okay, because when we differentiate u, we get something quite simple. We just get du is equal to dx, and the dv is going to be equal to sine x dx, and that means that v is going to be equal to negative cosine x. So therefore, our integral becomes uv, so uv is negative x cosine x, evaluated at 0 and pi by 3, plus the integral from 0 to pi by 3 of v du, so this is cos x dx. So if we evaluate the first term, we get negative pi by 3 times cosine pi by 3. And if we evaluate the term at the lower limit of 0, we obviously get 0. Now we calculate this integral, so this will give us sine x evaluated at 0 and pi by 3. And now what we're going to do is evaluate cosine pi by 3. So cosine pi by 3 is a half. And then we have sine of pi by 3 as well, and we're evaluating the second term, and again at the lower limit we get 0. So this gives us negative pi by 6 plus sine of pi by 3, and sine of pi by 3 is root 3 divided by 2. So that's our answer. And so here, if you weren't sure how I got the values for sine and cosine at pi by 3, the easiest thing to do is draw a right angled triangle, the opposite side equal to 1. This angle is 30 degrees, this angle is 60 degrees. Then if you fill in the lengths, they are 2 and root 3, which gives you the values of sine and cosine respectively. Okay, so moving on to our second integral. So now we have the integral of x to the 5 times e to the negative x cubed dx. And looking at this integral, the first thing that you notice is that the term that we don't like in this integral is the e to the negative x cubed term. Okay? So this is a good candidate for substitution. And I'm going to move my triangle up a little bit here, just to give myself some more space. And so the substitution we're going to make is we're going to set w to be equal to negative x cubed. Okay? So that gives us, let's do a little bit of work on this, that gives us dw is equal to negative 3x squared dx. And you'll notice that in the integrand we have x to the 5 dx. So what we're going to do here is we're going to multiply our left hand side by w, and we'll divide by negative 3 as well. So now on the left hand side we have negative w dw divided by 3, and you'll notice that that becomes x to the 5 dx. So therefore our integral becomes negative w divided by 3 times e to the w dw. So this is negative 1/3, taking the constant outside, w e to the w dw. So now if we look at this, this is another integral that we want to solve by parts. So let's set u to be equal to w and dv to be e to the w dw. So therefore du is equal to dw and v is equal to e to the w. So now what do we get? Using the integration by parts formula, so we get negative 1/3 times by uv. So uv is w e to the w minus v du, which is the integral of e to the w dw. What does that give us? That gives us negative 1/3 times by w e to the w minus e to the w plus an arbitrary constant. And there's one final step that we need to do whenever we do an integral by substitution. The final step is to substitute back for our original variable x. So remember that w was negative x cubed, so we get negative x cubed e to the negative x cubed minus e to the negative x cubed plus a constant. And there we go. So moving on, let's do another integral. So now we have another indefinite integral, and this is of the form the integral of cos x divided by sine squared x minus sine x. So first thing we're going to do here, let's factorize. So this is cos x times by sine x times sine x minus 1 dx. And now let's do a substitution. Let's set u equals sine x. So here we're doing a trigonometric substitution. With u equals sine x, we get du is equal to cos x dx. So things are working out nicely because we have a cos x on our numerator. And indeed, now once we do the substitution, this becomes the integral of 1 divided by u times u minus 1 du. So now we have to tackle this integral, and what we recognize here is that this is a rational function. So we should tackle it by expanding in partial fractions. So let's write 1 over u times u minus 1 as a over u plus b over u minus 1. And let's work out what the factors a and b are. So to find a and b, we multiply up. And that gives us that 1 is equal to a times u minus 1 times plus b times u. So now we compare coefficients. On the left-hand side, our u coefficient is 0. So we get 0 is equal to a plus b. And on the left-hand side, our constant coefficient is 1. And on the right-hand side, our constant coefficient is negative a. So therefore, a equals negative 1, and b is equal to 1. So now we go back to our integral, and we have the integral of negative 1 over u plus 1 over u minus 1 du. We know how to integrate both these terms. So the first term is ln of absolute value of u. The second term is ln of absolute value of u minus 1 plus an arbitrary constant. Final step, because we made a substitution, substitute back our original variable. So this is, first term is negative ln absolute value of sine x. Second term is ln absolute value of sine x minus 1 plus an arbitrary constant. And there we go. All right, for our fourth integral, we have another indefinite integral, and this is ln tan x divided by sine x plus cos x. So again, this is an integral that we're going to do by substitution. And the substitution that we're going to make in this case is u is equal to ln tan x. So if we calculate du, well, by the chain rule, we have 1 over tan x, because the derivative of ln t is 1 over t, and then we multiply by the derivative of tan x, which is sec squared x dx. So let's simplify this a little bit. 1 over tan x is cos x divided by sine x. And by definition, sec x is 1 over cos x, so we have 1 over cos x squared du. So we can cancel some of these terms, and what we end up with is du is equal to 1 over sine x cos x dx. And so lo and behold, what have we found? We found that our integral, or our integrand, when we rewrite it using the substitution, becomes the integral of u du. So now we can integrate this. This is 1/2 u squared plus an arbitrary constant. And then we apply our substitution. So this is the ln tan x all squared times 1/2 plus an arbitrary constant. And that gives us our solution. Okay. So, moving on, we now have a series of true or false questions. So, first question, the antiderivative of x squared plus x plus 1 divided by x cubed plus 1 involves an arctan term. So we're asked here to answer whether this is true or false and also justify our answer. So first of all, let me give the answer. This is true. And now let's see why. Okay. So the first thing I'm going to do, let's factorize our denominator. So x cubed plus x is equal to x times x squared plus 1. And notice that we've now factorized this into a linear factor, that's x, times by an irreducible quadratic factor, that's x squared plus 1. So the quadratic x squared plus 1 has no real roots. So now we take the partial fraction expansion. And this takes the following form. This takes the form a divided by x plus bx plus c divided by 1 plus x squared. Let's expand this out a little bit more. So this is a divided by x plus bx divided by 1 plus x squared plus c divided by 1 plus x squared. And if we are actually calculating the integral, here we would need to find the values of a, b, and c, which we would do by multiplying up and comparing coefficients. But in this case, we actually don't need to do that. What we notice now is that we have this term here, okay, and this is what's going to give us the arctan. So this term gives an arctan when integrating. So the important thing to keep in mind here is the right form for the partial fraction. So here we have a rational function. We first of all factorize the denominator into our linear and irreducible quadratic factors, and then keep in mind that this is then the right form for the partial fraction expansion. Okay, second true or false question. The integral of 1 over x cubed from 1 to infinity converges. So, this is also true. And the way in which we are going to determine this is to work directly from the definition of an indefinite integral and via using the limit. So by definition, this is an integral where the upper limit is infinity, so it's defined as the limit as t tends to infinity of the integral from 1 to t of 1 over x cubed dx. So this is the limit as t tends to infinity of negative x to the negative 2 divided by 2, evaluated at 1 and t. So this is the limit as t tends to infinity of negative 1 divided by 2t squared plus 1/2, evaluating this at the lower limit. And as t tends to infinity, t squared tends to infinity, 1 over t squared tends to 0. So what we're left with is 1/2. Okay? So the limit exists. So the limit exists, therefore the integral converges. And keep this in mind, we'll be coming back to this, this type of integrand in a little bit later in the lecture. Before we do that though, we're going to move on to a different type of question. We're going to be where here we are interested in calculating areas of certain shapes. Okay. So we've seen a variety of different techniques to do this. Here we're going to focus on setting up the integral in the usual way and then working out how to evaluate it. Okay. So first thing we're going to do here, let's draw our shape. So our shape is an ellipse. And if you notice here, when x is 0, so let's work this out. If x is equal to 0, then 4y squared is equal to 36. So therefore, y squared is equal to 9. So therefore, y is equal to plus or minus 3. So that's this point here and this point here. And when y is equal to 0, then we have 9x squared is equal to 36. So therefore, x squared is equal to 4. Therefore, x is equal to plus or minus 2. So we're asked to evaluate the region, find the area of the region inside the ellipse for x between 0 and 1. Okay, so here's x equals 0, here's x equals 1. So let's draw a dashed line. So this whole thing is our region. Okay. Let's give this a name. Let's call this A. Okay. So let's do a couple of things. So next thing I want to do, let's rearrange the equation for our ellipse here. So I'd like to find the equation of this curve here. And let's find this as an expression expressing y in terms of x. Okay. So if I have 9x squared plus 4y squared equals 36, this tells me that 4y squared is equal to 36 minus 9x squared. And this tells me that so this tells me if I now divide by 4, I am let's take out the, so I have, let's factor out a 9, so I'm left with 9. Y squared is equal to 9 divided by 4 times by 4 minus x squared. So therefore y is equal to 3 over 2 times by square root of 4 minus x squared. Okay, and this is the upper curve. So our area, by symmetry, our total area A is equal to twice this area, which is the area under the curve. So now now that we've worked out the equation for the curve, we can write this as the integral from 0 to 1 of 3 over 2 times by square root of 4 minus x squared dx. And notice, as I said, we have the 2 here because our area is both the top half here, which is the integral, and the bottom half here, which is its mirror image. Okay, so this is an integral. Let's simplify the constants. So we get 3 times the integral from 0 to 1 of, let's write this as 2 squared minus x squared. So this is the type of integral you'll recall from earlier in the class that you wish to solve by a trigonometric substitution. Okay? Because this is of the form a squared minus x squared, we'll use a trigonometric substitution. And the substitution we're going to use is x is 2 sine theta. So what does this give us? First of all, our dx is equal to 2 cos theta d theta. And when x is equal to 0, theta is equal to 0. And when x is equal to 1, theta is equal to arc sine of 1/2, which is equal to pi by 6. So our area becomes 3 times by the integral from 0 to pi by 6 of the square root of 2 squared minus 2 squared sine squared theta times by 2 cos theta d theta. So what does this become? This is now 6 times by the integral from 0 to pi by 6. We can take out the factor of 2 squared, so we'll get 2. And we'll have the square root of 1 minus cos squared theta. So that's cos theta. And because we have our other cos theta term, we get cos squared theta here. So just to reiterate what I did here, we pulled out a 2 from here. That came out here. Then in here, we're left with 1 minus sine squared theta, which gives us cos squared theta. We take the square root, we get cos theta, and then we combine it with this other cos theta to get cos squared theta here. So this is now 12 times the integral 0 to pi by 6. We have cos squared theta, so the way in which we integrate cos squared theta is to use the double angle formula. So let's write this as 1/2 1 times 1 plus cos 2 theta d theta. So we have 6 times by, now we integrate 1 plus cos 2 theta. So this is 1 plus sine 2 theta divided by 2, evaluated at 0 and pi by 6. Let's evaluate this. So we have 6 times by theta. So at pi by 6, this gives us pi by 6 plus sine of 2 theta. So that's pi by 3 divided by 2. And notice that at 0, both theta and sine 2 theta are 0. So what does this become? This becomes pi plus 3 times sine pi by 3, which is pi plus 3 times root 3 divided by 2. And if you go back to the first question, you'll see the calculation of sine pi by 3. Okay, so the key thing to take away from this question, there are several components. So first of all, rewriting the area as we did here as an integral. And then secondly, recognizing when you have an integral where the integrand looks like this, that this is a candidate for trigonometric substitution, and because it's of the form a squared minus x squared. And so the right substitution here is x equals a sine theta. Once you've done that, you end up with a standard trigonometric integral, in this case cos squared theta, and the rule for that is that you use the double angle formula. Okay, so let's move on to our next question. So, this next question, we're moving on to numerical integration, and we're going to talk about Simpson's rule. So we're going to use Simpson's rule to approximate the integral from 0 to pi of sine x dx. So first thing I want to do here, let's just draw a little picture to illustrate what's going on. So here's sine x between 0 and pi. And we're using n equals 4. Okay. So this is pi, this is 0. So in this case, our delta x is b minus a over n in general. So this is pi divided by 4. So this gives us our values for x0. x0 is of course 0. x1 is pi by 4. x2 is pi by 2. x3 is 3 pi by 4. And of course x4 is pi. So here's pi by 2, here's 3 pi by 2, 3 pi by 4, and here's pi by 4. So this is x0, x1, x2, x3, and x4. And I'm just going to draw in the function values here as well. Okay, so now Simpson's rule is delta x divided by 3 times by f of x0 plus 4f of x1 plus 2f of x2 plus 4f of x3 plus f of x4. So you remember with Simpson's rule, we have the terms at the endpoints, so that's f of x0 and f of x4. Then all the other terms, so the odd terms, so here f of x1 and f of x3 get multiplied by 4, and the even terms get multiplied by 2. So, what's this? We worked out our delta x, that was pi by 4, so this becomes pi by 12. And now we have sine of x0, which is sine 0, plus 4 sine of x1, which is sine pi by 4, plus 2 sine pi by 2, plus 4 sine 3 pi by 4, plus sine of pi. So, let's go ahead and calculate this. This is pi by 12 times by 0 plus 4. Sine pi by 4 is 1 over square root 2 plus 2 times by sine pi by 2, which is 1, plus 4 times sine 3 pi by 4, which is 1 over square root 2, plus sine pi, which is equal to 0. So what we get here is pi by 12 times by, let's simplify the term, so let's take 2 here, plus 8 divided by square root 2. So here my 2 is coming from here, and then my 8 divided by square root 2 is coming from these two terms here. And let's do one more thing to simplify this. So we get pi by 12 times by 2 plus 8 divided by 2 root 2, which is 4 square root 2. And let's pull out a factor of 2 as well. So we get pi by 6 times by 1 plus 2 square root 2. And that's our answer. So when you're doing a question like this and you get to this stage, it's always worth doing the extra few steps just to simplify your expression as much as possible. So a couple of things to keep in mind in this question. So first of all, delta x, the calculation that we use here is b minus a over n. That gives us the values for our xi's. Okay, so xi is x0 plus delta x times I. Then the formula for Simpson's rule as we discussed. Keep in mind that with Simpson's rule only is valid when n is even. Okay, so we couldn't have asked this question with n equals 5. N has to be an even integer. And then the rest of it is algebra. Okay. Now, moving on. So now we're going to talk about an improper integral. So we've already seen one. Now we're going to look at a different type of improper integral. So this is the integral from 0 to 4 of ln x divided by square root of x dx. So, first thing to say, this is improper since the integrand is not defined at x equals 0. Okay, so in this case, both ln x and 1 over square root x are undefined at x equals 0. So therefore, this is equal, we define this integral as the limit of the integral as t tends to 0, and it tends to 0 from above, of the integral from t to 4 of ln x divided by square root x dx. So, to evaluate this integral, we first need, to evaluate our original integral, this thing, we first evaluate this integral, and then we take the limit as t tends to 0 from above. So we need to calculate this integral here, and again, we're going to do this by parts. So I'm going to take u is equal to ln x, and dv then becomes dx divided by square root x. Why did I do this? Well, whenever we do integration by parts, we are generally looking to set u such that when we calculate du, we get something simpler. So in this case, our du is 1 over x dx. And in this case, our v is equal to 2 square root x. So what we have here now is the limit t tends to 0 of uv, so this is 2 ln x square root x, evaluated at t in 4, minus the integral from t to 4 of v, which is 2 square root x, du. So that's 1 over x dx. So this is the limit as t tends to 0 of, well, let's evaluate our first term. So at the upper limit we get 2 times ln 2 times square root 4, which is 2, minus 2 times ln t times square root t. Right, that's what we get at the lower limit. And now our second integral. So we do a little bit of simplification here. So we have square root x divided by x, so that becomes 1 divided by square root x. So if we integrate, we'll get 2 square root x, and we have another factor of 2 sitting in here. So we get minus 4 square root x evaluated at t and at 4. So what do we have here? We have limit t tends to 0 from above. First term is 4 ln 2 minus 2 ln t, and I'm going to now write this as divided by t to the negative 1/2. The reason I'm going to do this is because we're going to use L'Hopital's rule to evaluate that limit. Okay, so then the second term now becomes 4 square root 4. So this is 4 square root 4 is 4 times 2, which is 8. And then minus the second term, which is 4 square root t. Okay, so now we can use standard properties of limits. So the first thing we know about a limit is the limit of a constant. Well, firstly, the limit of a sum of terms is the sum of the limits. So we can separate this into different terms. The limit of a constant is a constant, so we can pull out all the constant terms. So we have 4 ln 2 minus 8 minus 2 times the limit from t tends to 0 of ln t divided by t to the negative 1/2. So here I'm also using the fact that the limit of a constant times a function is equal to the constant times by the limit of the function. That allows me to pull this 2 outside. And then finally we have plus 4 times the limit as t tends to 0 of square root t. So this this final term here is equal to 0. Okay? So square root t as t tends to 0, that also tends to 0. So we have 4 ln 2 minus 8 minus 2. And for this second limit here, we're going to apply L'Hopital's rule. So L'Hopital's rule says that if I have the limit of f of t divided by g of t, for which both the limit of f and the limit of g is undefined, then this is equal to the limit of f prime divided by g primed. So f primed is 1 over t, and g primed is negative 1/2 t to the negative 3 over 2. And so now what we have here, I'm going to move on to the next page. So this is 4 ln 2 minus 8 minus 2 divided by negative 1/2. Let's pull the constant outside. Limit as t tends to 0. And we have 1 over t divided by t to the negative 3 over 2. So let's multiply up by t to the 3 over 2, which gives us t to the 1/2. And so this is now also equal to 0. So all I did here from going from here to here is I multiplied up by t to the 3 over 2 in my denominator and my numerator. I got t to the 1/2. The limit of that is equal to 0, so we are left with 4 ln 2 minus 8. And that's it. So the important things to note here about this problem, so first of all, this is an improper integral. So the first thing we do is we figure out where the problem occurs in this integral. And in this case, it occurs at 0. Because 0 is the lower limit, then this integral is defined. We replace our lower limit 0 by a number t, and we take the limit as t tends to 0 from above. Then the rest is calculating the integral, and then finally we end here with applying standard properties of limits. And I forgot to write here that in this stage we were using L'Hopital's rule. And I guess there's a hat there as well. Okay, so let's move on to our next problem. So in this problem, we are talking, we're talking about population models. Okay. So we spend a bit of time modeling populations. And so in this example, we have a population y, depending on t, okay? And this population is being harvested. Okay? So, and the model that we have to model the change of population as it's harvested is this. So y primed of t is equal to 0.008 y minus h. Okay. So the idea here is that 0.008 is the growth rate of the species, and h is a constant, a positive constant, which is the annual harvesting rate. Okay. Finally here, y0 is the initial species population. So the species is growing with this constant of proportionality, and every year h units of the species are being harvested. Okay, so we have a negative h. So, first question, if y0 equals 2000, what harvesting rate should be used to maintain a constant population of y equals 2000 for all time? Okay. So, a constant population means y primed equals 0 for all t greater than or equal to 0, i.e. 0.008 y minus h is equal to 0, and for all t. which is equivalent to y, which is equivalent to h is equal to 0.008 y. This holds for all t. So if we set t equals 0, this implies that h is equal to 0.008 times y0, which is 0.008 times by 2000, which is 16. So therefore, h is equal to 16 units per year. Okay, so that was part A. And now for part B. And part B, it's really the same idea. So here we're told what the harvesting rate is. So if 200 units per year are harvested, we're asked what initial population ensures that you have a constant population over all time. So if you're interested if you're doing harvesting, both of these are interesting questions that you might want to ask, because you would generally, if you're harvesting, don't want your population to shrink and you don't want your population to blow up. So here's the same idea. So we want y primed equals 0 for all t. So therefore 0 is equal to 0.008y minus h. We know what h is. H is 200. So if we rearrange, this says that y is equal to 200 divided by 0.008, which means that y is 25,000 units. Okay. So one thing to take away from this question, notice that to answer both of these questions here, we didn't have to calculate the solution of the differential equation explicitly. We just looked at when y primed is equal to 0. Okay. But in doing that, we've in fact calculated, so in part A here, you're in fact given the solution, it's y equals 2000. In part B here, again, we found the solution of the differential equation in this case, which is 25,000. Okay. Finally, one final question to conclude this lecture. We're going to come back to this question of improper integrals, and we are going to come back to this important topic of integrals that take the form the integral of 1 over x to the p for x between 1 and infinity. And this is a very important special case. We haven't talked about it in the review class, but we talked about it in lectures. These are the kind of integrals that you use very frequently when you use the comparison theorem to try and work out if a more complicated integral is convergent or not. So often what you do with the comparison theorem is you try and relate your integral to something like 1 over x to the p. So the procedure is exactly the same for this integrand. For this integral. So we write it the limit as t tends to infinity of 1 over x to the p dx from x equals 1 to x equals t. And now we need to calculate the antiderivative of 1 over x to the p. And I'm going to assume here that p is not equal to 1 for now. We'll deal with that case in a moment. And so then what do we get? We get negative x to the negative p plus 1 divided by negative p plus 1, evaluated at 1 and t. And this becomes the limit as t tends to infinity of t to the 1 minus p divided by 1 minus p plus 1 divided by 1 minus p. Apologies, that's the wrong way around. It's 1 divided by p minus 1. So, now, to determine whether or not the integral converges, we just ask whether or not this limit exists. So this limit exists. Well, we have our exponent of t here is t to the 1 minus p. So we're taking the limit as t tends to infinity. So for the limit to exist, we need this term here, 1 minus p, to be less than or equal to 0. So we need 1 minus p less than or equal to 0. So therefore, p is greater than or equal to 1. But we assumed p is not equal to 1. So therefore, p is greater than 1. Okay. And if p is less than 1, the integral diverges. So we've determined that when p is less than 1, the integral diverges, and when p is greater than 1, the integral converges. The only case that we need to look at is when p is equal to 1. So let's consider p equals 1. So then we have the limit t tends to infinity of the integral from 1 to t of 1 over x dx. This is the limit t tends to infinity of ln x evaluated at 1t. This is the limit as t tends to infinity of ln t minus 1. This does not exist, since ln t tends to infinity as t tends to infinity. So therefore, when p equals 1, the integral diverges. So, therefore, to summarize, the integral from 1 to infinity p equals 1 to x converges, and p is greater than 1, and diverges when p is less than or equal to 1. And that's it. Okay, so we have now concluded this lecture. The answer key is on the final page here. That concludes the review class for the midterm. Best of luck for the midterm. Make sure you study, you look back over all the past quizzes and homework questions. Solutions for the quizzes are on the Canvas page. Make sure you go back through all the exercises and you can do them and solve them efficiently. And then make sure you're ready for Friday's midterm exam.